Okay, so good morning, everyone. For today, we are going to continue with question number six, and then to question number seven, and then I think that will be the last class for the semester. And hopefully on Sunday, I'll be doing like maybe like a uh, depends, so like maybe a 2 or 3 hour session. But I'll only be answering questions that you guys submit to me. So I won't be doing any question papers or things like that. But if you have any questions, you can submit them to me and then I'll solve it for you. So starting with question number six, we have over here a coil that consists of 450 windings. Is is it possible to record the session? Yes, the session is recorded as well as the previous recordings, and I think I have posted like links to the recordings, so you can watch the recordings. I think I did question one, two, three, and four and five in the first recording, and then I think I did um, the other recordings five and seven in a different recording. So both links are on the group. Unfortunately, I wasn't able to do all the question papers and explain step by step, but I have posted the memo. So if you guys want, you can always look at the memo and then work from there. But Sunday we will have a short, like, depends how much questions you guys submit to me. So I'll be doing questions that you guys submit to me, and on Sunday I'll explain step by step on how to solve those questions. But the question needs to come from either the textbook or from past papers. So nothing hectic, because I know like lecturers just want to know if you guys understand how to solve questions instead of doing very complicated questions. If there is a possibility that there's like one or two questions that is very complicated because they want to separate those that get above 50 and those that get like distinctions. So there are a couple of questions that you need a deeper and much broader understanding of the chapter. So to not waste any more time, let's start with the first question that we have here. And the question says, a coil that consists of 450 windings. So um, if you guys remember from our last tutorial, physical tutorial session, is that we had to draw like coils and stuff, right, and had windings around them. So if you haven't forgotten about that, I advise you to go over each chapter before, like before you write any test, go over each chapter and understand the basics before you go and write the question paper. And another question student asked me was like formula sheet. Like I'm not sure, and I don't feel like I should ask the lecturer about that. But the lecturer I had last year, he had given us like formula sheets. So this year I'm not sure if the new lecturer will give you guys a formula sheet or what. So it's best if you guys remember the formulas. And I think like for inductance and magnetism, he has to give those formulas because they are not easier to remember. So back to the question, a coil consists of 450 windings. So let's cite what we have. So we have 450 windings is wound around a base plate. So we have a ring, right? That's a keyword. The mean diameter of the ring is 100 millimeters, and the diameter of the ring is 20 millimeters. The current through the coil is 3 amps. So we have, so this here, right, is going to be the length because it's like the ring. So this distance here is 100 millimeters, right? So let's not forget about that. So we have the length of 100 millimeters. Next is diameter. So diameter is cross section of the wire. So this area here is the diameter of the wire, which is 20 millimeters. Let's do that. 20 millimeters. And we have a current of 3 amps, right? So determine the field strength, the field density, the total flux. Okay, so to answer this question, like the best way I would do it is instead of going to the formula sheet and looking for formulas, what most students forget that you can actually get marks for steps. So if you have the diameter and you calculate the area, you have a possibility of getting like at least 1 or 2 marks just for this area calculation. So let's start off by calculating the, the area of this thing. So the area is equal to pi over 4d squared, right? Oh, let me just go and fetch my calculator. I forgot it in the other room. But I have to convert this 20 millimeters to meters. So we have 0,02 squared. Okay. So the answer here, I'm just going to fetch a calculator. I'll be right back. Sorry about that. Let's start my calculator. Five, this, shift, 5. So pi divided by 4 multiplied by the diameter of 0.02 squared close the brackets equal to. So we have an answer of 310 times 10 to the negative 6 meters squared. So we know from this question that it says that it's a ring, right? So because it's a ring, we have to get, uh, sorry, this here, right? This 100 millimeters. It's not the length. Sorry, this is the diameter. So there's two diameters. So we have this diameter, and then we have this diameter of the wire. So this is the wire, and this is the loop. So we have two diameters. So the area is for the first diameter. So for the second diameter, we have to calculate the circumference. So the circumference is equal to the length, which is equal to pi multiplied by diameter. So we're going to use pi and a diameter of 100 millimeters, which is 0.1 meters. And if I punch that into my calculator, I get an answer of 5 multiplied by 0.1. I get an answer of 310 times 10 to the minus 3 meters, and that can be converted to 0.31 meters. You're basically going to take this negative and you're going to move it 1, 2, 3 decimal places. So now we have the length and we have the diameter of the loop. We are going to now calculate for the first question. The first question wants us to calculate the field strength. And if we look on the formula sheet, field strength is equal to H, right? For strength is equal to the current times the number of windings over the length. Okay, so the first question is field strength. So the field strength is equal to current multiplied by number of windings over the length of the ring. So we have a current of 3 amps. We have 450 windings. So basically what they mean is that you're going to take a copper wire and current going to flow through here, and we have a ring where we have this windings around this ring. So we have these windings over here, and these are like 450 of them. And we all know that for magnetism that if we increase the number of windings, we are going to increase the strength of the magnetic strength. So you can see from this formula that if we increase the windings, the strength increases. So that is what like engineers try to do when they want to increase the strength, or if they want to decrease it, they decrease the number of winding, or they decrease the current, and then they get a decrease in strength. And I remember someone asking me in the first physical tutorial session. He asked me like, "What is this even used for?" And actually, I didn't know at the time, but then I did my research and I found out that these are used for like to convert electrical to mechanical and mechanical to electrical. And the reason for that is that you want something that would work as a safety device for faults. So if there's a fault, you want something physical to happen, and that's why they created this devices where the magnetic would what you call this repel and attract certain metals that would like open and close circuits in safety devices. I think there's one in your breaker. So at home, you would see in your breaker one of these safety devices. So continuing with the question, we're going to take the length. So this is 0.31, and this length is the length right around the complete distance. And remember, sometimes you can even have an A gap over here. And don't be confused, don't add those lengths. You have to do it separately, completely separate. Do not add the length to get the total length. This is not the total length. This is only the length of the material itself, this here. So continuing with the field strength, if I punch it in my calculator, I'll get an answer of apparently my calculator is not working. Let me use the one on my cell phone. So we have 3 times 450 divided by 0.31. Answer, we have an answer of 4299 amps per meter. So remember that this amps and this meter. So amp meter. I think they give you like half a mark or 1 mark if you don't put this unit in. Most likely even zero. Depending on the lecturer, you might just ignore if you don't have units. So make sure for electro and physics and fluids that you have the correct units in there. Okay, so we're going to write the electric field strength is equal to 4299 amps per meter. The next is our most serious flux density, and we know that um, the flux density from our triangles. We normally have a triangle, right? I like triangles, easy to remember, but I think it might just be on your formula sheet. And we know that the charge will equal to the magnetic density multiplied by the area. So let's calculate the magnetic density. No, wait, what's the question? The question says flux density. Flux density. So they want B Tesla, right? They want B Tesla. So they don't want this. So okay, so another thing to note is that we have to solve this question before we move on to the next question. So we solve the field strength, and we can use the field strength to get the permeability of the material itself, or get the permeability of the A gap. So I think mu of A multiplied by mu of the material is equal to the density over field strength. So we're going to ignore this one, and we know that this one here is a constant of 4 pi times 10 to the negative 7. So I think we can solve for B, the, the one for B, flux density. So B, magnetic density is equal to the permeability of A multiplied by the field strength. So why do we use A? Remember that around this device there's A here, right? And it's quite different for permeability of the material. So we see, like for this question, they haven't given us the permeability of the material, so we can assume that the permeability is equal to 1 because it's not given. So we can just say that it's not completely cancelled. It's equal to 1. So it's going to this is equal to what? This is equal to 4299. So let's do the calculation for this is going to be 4 pi multiplied by 10 negative 7 multiplied by 1 multiplied by the field strength, and we get 4299 amps per meter. So let me just put that in my calculator. 4 multiplied by shift pi multiplied by 10 to the power of negative 7 multiplied by 1 multiplied by 4299 equal to. So we have an answer of 5.4 times 10 to the negative 3. So we have 5.4 times 10 to the negative 3 Tesla. Don't forget your units. I think this is easier to remember. Tesla, like Elon Musk, you know? So let's go back here. And we got how much? Let me go back to the calculator. 5.4 times 10 to the negative 3 Tesla. So you can write the full version or you can just write T, depending on what you prefer in the exam venue. So the next question is total flux. So we know for total flux is equal to the density multiplied by the area. And remember, we calculated the area over here, so that is your 1 mark. So the next mark is over here. So as we calculate this will be our second mark. Our density is 5,4 times 10 to the negative 3 multiplied by the area. Area is 0,31, and our answer over there would be, let's do this quickly, calculator, 5.4 times 10 to the power negative 3 multiplied by 0.31. So we got 1,7 times 10 to the minus 3 Weber. Or you can just write that. So that's pretty straightforward. Are there any questions? Oh, someone has their hand raised. Yes, sir.
Can you hear me, sir?
Yes, I can hear you.
Can you please show me the first question, A, where you calculated field strength? This formula.
Sure.
Yeah, this one.
Okay.
Okay. I'm getting in my calculator. I don't know if the problem is my calculator. Let me. When I'm calculating it, I don't get 4,299. I'm getting the other
Sure.
number.
Let me just double check. 3 times 450 over 0.31. Just double check this here. Do you get 4.4?
I'm getting 4,354.
4,354.83.
Yes, 0.83.
Okay. It's, let me just check. Okay. 310. Okay. It's still correct. It's just that where's this question now? It's just for the area year I rounded off, so that's why it's like, remember that pi is 3,14 and something
Mhm. Yeah.
147. So if you multiply that by 0,1, the actual answer is 314 something like that. So just by
Okay.
rounding off, let me just round this off to, did you got how much? 3.5. Then 450 over 0.31. Okay, so I'm getting 3,000. Wait, I'm actually getting 4. Wait, what is your answer?
This side I'm getting 4,354.838.
4, 3,
54.
5, 4. Okay,
Yeah.
so we just need to change it over here. Instead of 354. Like in exam, I think there is like a 5% leniency towards all of them. So you don't have to stress too much about getting the exact answer. Is that okay?
Yes, sir. Thank you.
Okay. So let's get the next question because we're done with this. Question 6.1. So this is the next question. Let me just screenshot this question. Okay, so this is the next question. And normally we would see students, they would normally just add this distance and assume that it's one material. But in actual fact, there's actually an A gap here. So we cannot add the limb, remember? And then this shape, let me just read the question. Okay, so they give you the cross-section area, so you don't have to worry about the shape, but the length over here, we have to, okay, let me just show you. Normally students would do this. They would add this length and the length of the A, and this is completely wrong. Reason be like it's 9 marks and it cannot be this simple. So sometimes it's best to check how much marks the question is before even solving questions. Like that's what I like to do. I like to check like if it's reasonable for the lecturer to give this many marks for solving a question like that. So let's start with this question. The question says figure 6 shows a relay. So okay, so another example is a relay switch, right? Which has two components, a fixed core and a movable armature. Assume that the A gap is 2 millimeters. So we have a length. So the length of the A is equal to 2 millimeters. When the relay is open, calculate the current required solenoid to produce a flux of 12 microweber. So we know that the Weber is 12 microweber. The length of the magnetic circuit is 20. So this is the first length of the material itself. This material over here going right around the completed length. And then we have a solenoid attached here. I think the solenoid reacts a certain way, right? Which opens and closes this part of the circuit. So continuing on with the question, the material of the core armature is cast iron. Okay, so they gave us the permeability. Okay, wait, sorry. Cast iron is the name. The relative permeability of cast iron. Okay, so the permeability is given over here. I thought I had to Google that. Uh, Turns of the solenoid. Calculate. Wait, turns on solenoid. Okay, so this is the number of turns here. So we're gonna have something like this going around there. Right. So what's happening here is you're going to put a current through this thing, and then it will cause like a magnet to attract and repel. So this thing will be either attracted or repelled depending on the current that's flowing through here. You just pick a different color, solenoid, like this. So we have about 1,000 turns. 12 microwavers. And okay, so let's write all the things that we have at the bottom. So we have flux, what do you call this thing? Flux, which is 12 microwave. Then we have a length 1 of 0.12 meters. Then we have the length of the A gap, which is 2 millimeters. 2 millimeters is equal to, okay, 2 times 10 to the minus 3 meters. Then we have the permeability of cast iron, 170, and we know the permeability of A from the previous question is 4 pi times 10 to the negative 7 from this question here. Where is this thing for A? That we have a number of windings, which is equal to 1,000. Then cross section area is given. So we have that, that one, wrote that, wrote that area, and we wrote that one. Area is equal to 240 millimeters, 4 millimeters squared. Is there anyone that knows how to convert millimeter squared to meter squared? Anyone in the group chat? Because, like, I think this is very, very important in applied strength, in thermal, in ELC, and a lot of people will get this wrong because normally they will give it in millimeters and things like that. So, if there's anyone that wants to help the students out on converting this, it will be great. Or else I'll explain to you guys because I think this question and this trap is set by all the lecturers. So it will be there for strength of materials, it will be there for thermals, it will be there for fluids. Because as an engineer, we only work with meters and things like that. We don't really use millimeters for our calculation unless you want your answer to be in millimeters, but preferably I like to use meters because every formula requires you to input it as meters, and using millimeters just complicates things. But they are like solutions where people use millimeters. So someone says you multiply by 10 to the power 3. Unfortunately, that is incorrect. You do not multiply by 10 to the power 3. Multiply by 10 to the power 3. Multiply by 10 to the power 3. Uh,
Multiply by 10 to the power minus 6.
okay, so yeah, so that is the correct answer. Thank you for sharing that. I'm not sure you're the same person, but that's how you normally do it. But I like to explain to you guys how and why because sometimes they don't just give you, you see, it's the same thing. It's not because you forgot the negative. Whereas if you did that, you would actually get a bigger answer instead of getting a smaller answer. So that negative sign is very important. Um, Continuing with the explanation is that because instead of millimeters, they might give you centimeters or micros or picos or hectares. So it's best to know your engineering notation. So we have engineering notation. Um, Guys, remember your engineering notations, right? So from your engineering notation, we're going to write, let me get a black pen, 24 millimeters squared. So we want to convert this to meters squared. So to convert that, we are going to the engineering table, and I think most of you guys have to memorize the engineering table. And for millimeters, we know that it's 10 to the negative 3, correct? So we're going to take the square and put it there, times 2 meters squared. So then we have an answer of 2, 4 times 10. So you know your laws of if the base is the same and exponents, you're going to have to multiply this out, right? So we get a negative 6 meters squared. So now that is our area. So I hope you guys understand that over there. That is the method I use. Let me just write it out a bit better. So we have 24. So millimeters is 10 to the minus 3. And then that 2 is transferred there. And then you get an answer of 24 times 10 to the negative 6 meters squared. So I think that will help you in almost all your modules, if I'm not mistaken. Um, Another thing about this thing, I almost forgot this thing. Okay, so like, so this one is area, right? So if you're given 24 uh, millimeters cube and you want to convert it to meters cube, you're going to take 24, go remember your engineering tables, 10 to the negative 3. You're going to move this to that side as well. So it's going to be 3 meters 3. So you're going to have an answer of 24 times 10. 3 times 3 is negative 9 meters cube. So this will be for fluids. And then I think for applied strength, it's going to be 24 millimeters to the power 4, normally for your eye, inertia, and things like that. And you must convert it to meters 4. You're going to take 24 and you're going to take 10 to the minus 3 and 4 meters 4, and you're going to get an answer of 4 times 3, 4, 8, 12. 24 times 10 to the minus 12 meters 4. Is everyone okay with that? So this here is for STL and applied strength. This one here is for fluids. Currently, this one here is for ELC. So also like if you want to use the other method of 10 to the negative 3 multiplied by 10 to the negative 3. Also, I don't know how, wait, am I breaking the rules? Okay, I'm not sure about this one. I prefer using it like this, and that's how I solve these questions of converting them to the right units. Are there any questions? So we have 24 times 10 to the negative 6 meters squared. So the first question, oh, it's only one question. They want us to, okay, show the relay which has the components of the calculate the current. Okay, so the question is they want us to calculate the current. They want us to calculate current. Let me just check on the formula sheet real quick. Formulas we were going to use. Okay, so there are two methods of solving this question. The first method is using the electric field strength and adding it. and the second one is using the reluctance and adding them. So let's use the reluctance, but you can use it the other way. Let me just get this formula. I've got this formula for field strength. Okay, so if you use the second method with the field strength, you are going to use this formula of H, number of windings, I, over the length. Oh, sorry. This is the formula that students are using and failing in. So this length, they use this formula and then they just add the length. They add these two lengths over here. They add it and then they substitute it over here. And they have this, they have that, and they calculate this one. And then they get current. That is absolutely wrong. And we have to add the strengths separately and then get the current, which is the other method. But we're going to focus on this method here of calculating from the reluctance, right? So let's do the first one. So the reluctance 1. What is 1? 1 is the material itself, right? So we're going to have the length over the permeability of A multiplied by the permeability of the material, and then we're going to take the permeabilities of both of them and we're going to multiply it by the area. So let's get that. So the length of this thing is with the thing. Sorry, normally students add this too. So let's get the length, which is 0.12 over the permeability of A. Permeability of A is 4 pi multiplied by 10 to the negative 3 multiplied by permeability of the material was given, how much is this? 170 multiplied by the area, and we get an answer of calculator is 0.21 over 4 multiplied by pi multiplied by 10 to the power negative 3 multiplied by 1.7 multiplied by the area of 24 times 10 to the negative 6, and we have an answer of 230 kiloamps per Weber. So we're going to repeat it for A. So it's going to be the length over the permeability of A, and then that's going to be cancelled because there is no material between that spacing, and then it's going to be the area again. So we have a length of 2 times 10 to the negative 3 over permeability of A is 4 pi multiplied by 10 to the negative 3 open brackets area, and we have an answer of, just correct this, 2 multiplied 2 multiplied by 10 to the power negative 3 over. So I'm getting an answer of 6,6 kiloamps per Weber. So these SI units are not coming from here, they are coming from the other formula of reluctance. Um, Let me just get the formula for you guys real quick. Okay, so this here is from the formula of reluctance is equal to the magnetic motive force over the current. So we know that if we get the units here, we're going to have, oh, it's the other way. Magnetic motive force over I, and then that's how we get the amps per Weber over here because it's derived from this here. Missing something. So so this question wants us to calculate the current, right? So we have 230 and 6,6. So let's add those two. So 2 is total. So the reluctance total.
Sorry, Fayaz.
Yes, sir.
You said the formula is S is equals to mmf over I, but then the
Yeah,
unit
that's what
units
confusing
for,
me.
units for I is amperes most, and
Yeah, yeah.
yeah, it should be Webb. Isn't the formula isn't the formula S is equals to mmf over the flux?
Um, wait, let's just see again. So you're saying it's MMF over the flux.
Yes.
Okay, yeah, then that makes sense. Thank you. Just double check. Reluctance. Okay, yeah, makes sense. It's actually the flux here and not the current. That's how they derive those units for reluctance. So continuing with the question, we are going to get the total reluctance because there is no material at this location here. Get a different color pen. So there's no material here, so that means we have to add it. So let's add this thing S1 plus S of A, and we have 230 plus 6 comma 6 times 10 to the 3, and we have an answer of sorry guys, let me just double check this quick. So we are getting 6 comma 6 times 10 to the 3, and over here I'm getting are you guys getting the same answer as me? so we're going to add, wait, okay, let's add this two together. Wait, okay, it's not combine the units. 230 plus 6,6 times 10 to the 3. 230 plus 6.6 times 10 to the power 3. Okay, so we have 6,8 times 10 to the 3 kilo amps. So we're going to use that formula that we said earlier, where the reluctance is equal to the magnetic motive force over the flux. Sorry, over the flux. So we're going to manipulate this formula. So the magnetic motive force is equal to the flux multiplied by the reluctance. So we have nothing, the flux is given to us 12 micro. So we're going to take 12 micro Weber multiplied by the reluctance, the total reluctance, which is 6,8. So 3 and 3. So we have 10 to the 3, and kilo is times 10 to the 3 also. We have 6,8. 6,8 times 10 to, no, mega amps per Weber. So micro is 10 to the negative 6, and then mega is 10 to the 6. So those are going to cancel each other out, and we're going to have 12 times 6,8. 12 multiplied by 8. So we have an answer of 69 amps. So are there any questions? Oh wait, 6,8. We know the formula for this is equal to the number of rotations multiplied by the current, and we want to get the current, right? So 12 12 ish, 12 multiplied by 6.8, 6 8. So we get this is actually 68. We convert it there. 8, 68. So we have an answer of 0, 820. The magnetic motive force, and we need to find the current. So magnetic motive force is equal to the number of windings multiplied by the current. So current is equal to the magnetic motive force divided by the number of windings. And we have 820 over the number of windings, which is 100. And we have a current of 820 over 100, which is equal to 8,2 amps. Is your answer, guys? Are there any questions? I think that will be the end for the lesson. After at about two, we'll continue with question number. I think it's question number. The next question. So, are there any questions? So we finished all of this, question 6. So at 2 p.m. we will be doing question number 7. I hope you guys filled out the register before you guys sign out. Thank you and goodbye. I'm sorry, not goodbye, but see you at 2.